Hello, my name is Felipe and I am a master's student at the National Institute of Telecommunications in Atel. My work is called Defect Detection in Printed Circuit Boards based on EdgeML and computer vision. The co-authors are Iago, Rodrigo, and Professor Felipe. Introduction: Importance of quality control in PCBs. Nowadays, a large part of industries relies on products that use electronic boards or PCBs. Making sure these boards are high quality is key to delivering reliable products that meet customer expectations. Challenges in traditional quality control. Traditional quality control usually depends on manual inspections and sampling, which rely on human judgment. This can lead to mistakes and might miss defects not included in the samples. Industry 4.0. Industry 4.0 is transforming quality control with technologies like IoT, artificial intelligence, and cloud computing. These tools make processes more efficient and reliable. Objective of the work. This work aims to explore different CNN architectures to identify and analyze assembly defects in PCBs, focusing on industrial process. Current scenario and challenges. Manual inspection of PCBs. Manual PCB inspection is based on sampling, which increases the chance of missing defects. It also relies on visual checks and the operator's experience, making it more likely to have errors and inconsistencies. Risks in quality control. Quality control risks include missed defects from subjective inspections and reliance on operators, who can be affected by fatigue or lack of training. Impact on final quality. Defects in quality control can harm product reliability, leading to customer dissatisfaction, financial losses, and rework. Technologies used. Benefits of machine learning. Machine learning offers powerful benefits for quality control. It can process large amounts of data and automatically detect patterns in PCB images. Optimization of the inspection process. Optimizing the inspection process means accurately detecting defects, like missing or misaligned components, while reducing the need for manual inspections. Proposed architecture. Here in the image, you can see the proposed architecture. It is used a Raspberry Pi 4B running the machine learning model to process images receiving from the camera. The dashboard is planned for future work. Related works. The first work is called PCB defect detection with computer vision, Raspberry Pi. It focused on identifying manufacturing defects in PCBs, such as short circuits, open circuits, and missing holes. It used MobileNet version 2, YOLO version 5, and FOMO models. FOMO was the most efficient model, but did not explore weight quantization techniques or create specific dataset for assembly. The second work is called a real-time defect detection in printed circuit boards applying deep learning. It investigated PCB defect inspection using deep neural networks, ResNet 50. It achieved high accuracy, 96.29% under good lighting conditions, and used more robust hardware, for example Jetson Nano, without considering low cost and low power devices. Methodology. Here we can see an image showing all the steps that we used in methodology of the work. The first and second step is the definition of the industrial scenario for quality control. The next step is dataset creation and preprocessing. The fourth step is training of YOLO version 8, FOMO, and MobileNet version 2 models. The next step is model analysis and selection, and the last one is discussion of the obtained results. Dataset. Here we have an image showing the steps of the dataset creation. First, capturing PCB defects. Second, image collection. Third, data augmentation. And fourth, final dataset. Dataset construction. The dataset was created from images of PCBs with simulated defects. We use four defined classes in the work. Q missing, that means missing transistor. CI missing, that means missing integrated circuit. C13inv means inverted capacitor, C13. C19inv, that means inverted capacitor, C19. Total quantity. A total of 240 original images were expanded to 576 images after data augmentation. Data augmentation. It was used the platform RoboFlow to apply data augmentation to the dataset. The techniques used were rotation, horizontal and vertical flipping, and brightness adjustment. Importance of data augmentation. Data augmentation boosts dataset diversity, helping models generalize better across different scenarios. Evaluated architectures. The first one is YOLO version 8. It is an advanced model for high-speed object detection and delivers high precision but demands greater computational power. The next one is FOMO, designed for resource-constrained devices, focused on efficient and compact detection, ideal for real-time applications. And the last one, MobileNet version 2, lightweight network designed for efficiency on limited hardware. It offers lower precision compared to the other tested models. Here we have the evaluation metrics. The first one is precision. That is the proportion of correct predictions among those classified as positive. Measures the model's reliability, and the formula we can see here. The next is recall. That is the proportion of positive examples correctly identified. Indicates the ability to detect all defects. The third is F1 score. It is the harmonic mean of precision and recall, balances the trade-off between these metrics. And the last is mean average precision, or MAP. Average precision across different confidence thresholds. Assesses the overall performance in class detection. Here we have YOLO V8 results. For the non-quantized model, float32, we have computational performance. Model size 22 megabytes, CPU usage 30%, RAM usage 670 megabytes, inference speed 0.2 frames per second. And the metrics: precision of 96.8%, recall 92.7%, F1 score 94.6%, MAP 96.1%. For the quantized model, int8, we have computational performance. Model size 11 mega, CPU usage 20%, RAM usage 550 mega, inference speed 0.3 frames per second. And we have metrics: precision of 94.3, recall 94.8, F1 score 94.5, and MAP 95.6. As we can see, the quantization significantly reduced resource consumption with minimal impact on precision and recall. FOMO results. For the non-quantized model, we have computational performance. Model size 152K, CPU usage 25%, RAM usage 250 mega, inference speed 10 frames per second. Metrics: of precision 97%, recall 99%, F1 score 98, MAP 99. For the quantized model, we have computational performance, model size of 91K, CPU usage 20%, RAM usage 230 MB, inference speed 20 frames per second. And the metrics are identical to the non-quantized model. As we can see, FOMO achieved the smallest model size and highest speed performance. Here we have MobileNet version 2 results. For the non-quantized model, we have computational performance. Model size 11 MB, CPU usage 30%, RAM usage 350 MB, inference speed 3 frames per second. And the metrics are precision 61%, recall 87.5%, F1 score 71.8%, and MAP 100%. For the quantized model, we have computational performance, model size 3 MB, CPU usage 25%, RAM usage 300 MB, inference speed 6 frames per second. And the metrics are precision 55%, recall 79%, F1 score 65, MAP 65%. The results show that MobileNet was the least accurate among the evaluated models. Discussion of results. Comparison. FOMO outperformed prior studies, achieving a strong balance of high precision and low resource consumption. YOLO version 8 demonstrated greater robustness compared to older models, but required more computational resources. MobileNet version 2 delivered inferior performance, highlighting its limitations in complex scenarios. Key factors influencing results. Dataset. The creation of a specific dataset for assembly faults was crucial to the results. Capture conditions. Variables like lighting and PCB positioning likely impact the metrics. And quantization. Improved computational efficiency without significantly compromising precision, particularly for FOMO and YOLO version 8. Key conclusions. FOMO achieved the best overall performance, combining high precision, low resource consumption, and speed, making it ideal for constrained devices. YOLO version 8 delivered high precision but is less suitable for hardware with limitations due to its high computational demand. MobileNet version 2 resource efficient but showed limitations in precision and recall. Importance for quality control. Quality control is all about reliability, and this work shows how machine learning can make PCB inspections automated and consistent. It combines precision with efficiency, opening up new possibilities for real-world applications. Future work. Dataset expansion. Increase model robustness by expanding and diversifying the dataset. Real-world testing. Conduct evaluations in real industrial environments. And the dashboard development. Build an interactive dashboard enabling real-time monitoring and analysis. And here we have the references of the work. Acknowledgements and questions. This work was partially funded by Intelbras ProEducar program, CNPq and FAPEMIG, XG Mobile, Embrapi, Inatel Competence Center on 5G and 6G network, and a recognition to the collaborators from Y Lab, Inatel, and São Carlos School of Engineering, USP. Thank you for your attention, and I am available for questions and comments.